Okay, we are discussing boundary layers and external flows, and we're arriving the highest point of this class, in which we're putting together all the concepts together that we learned from week 1 until last week. So this is perhaps the most complex part of the class, because we need to have mastered everything so far to put it together and make sense. The good news is not too far from now, we'll just be learning formulas for plug and chug that will be a lot simpler. But the beauty is here. The insight is here, the understanding is here. And for those of you who dream about making new machines, making new inventions, understanding things that are difficult for pretty much anybody else, this is the key to much of that when it comes to heat transfer. So I took a look to a cool video that I think you're gonna enjoy, that is about boundary layers. Let me see if I can put it in the right size here. There we go. So let's see. Share sound. Okay. So this is a video done like long ago, and you're gonna realize pretty soon how long ago it was done. It's about boundary layers. This is about the fluid mechanics aspect of the boundary layer, which you have already been exposed in your fluid mechanics class. But I want to put it here so you visualize it, and hopefully you'll have a picture in your mind about these boundary layers. Okay, so let's do it. Here we go. And we have to go to 2.2.07. Is this older water?
This drawing, derived from potential flow theory, shows how, before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone. These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timelines, the vertical patches of bubbles, remain perpendicular to the streamlines shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the shearing forces and...
Okay, one thing. He mentions vorticity. We're not going to be worrying about vorticity here. All I want you to see is that if we have a flat plate, which few things are just a flat plate, but if we understand the flat plate, we can extrapolate this to pretty much any other geometry, because the concept is very universal. What they are showing is that the fluid that is very much, this is laminar fluid, you see there is no turbulence anywhere, and this fluid that is undisturbed, when it founds the plate, the fluid gets stuck. It's like because of the properties of viscosity. And that's why these layers drag along the surface. And you get to see how there's a significant change. These bubbles, let's make these bubbles up here, they don't know there's a plate. These don't know. But these bubbles out here, you can see how some got stuck here. And as we go farther and farther, they get dragged out. So this shape you see here is very much a representation of the velocity profile. So here velocity is kind of zero, and velocity increases, and these bubbles out here are proportional to the velocity of the free flow.
pressure forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected.
You see, it mentioned that outside the viscous boundary layer, the shear layer can be neglected. Shear is transport of momentum by viscosity. So it's like when we talk, is the analog of transport of heat by conduction. And we're gonna see that far away from the boundary layer is all about advection. We don't need to worry about conduction. But in the boundary layer, it's going to be all about conduction. Is this same analogy with fluid mechanics?
The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth.
Super important. He's talking about the boundary layer growth. In our first week of class, we discussed about Eulerian and Lagrangian coordinate frames. That are crazy words, right? And that we so seldom use. But this is a story. In these videos we had before, let's see. In this
the thickness
case,
of the boundary layer increases.
In this video that I just stopped, the fluid is moving, the plate is not moving, right? So this is an Eulerian coordinate frame in which we're fixed to the plate and the fluid just moves. So if we were to make, let's see, if we were to make a control volume around this rectangle here, yeah, I cannot format it much more, but if for the fluid, right, we see that the fluid moves through the control volume. Because it moves through the control volume, there will be advection, heat transferred by advection in the case of the thermal boundary layer, right? And this is because the fluid is moving, the control volume is not moving. This is what is called the Eulerian coordinate frame. That is what we use very often. But today, we're going to also look at things from the point of view of the Lagrangian coordinate. Lagrangian coordinate frame.
Is the distant fluid deceleration bubbles generated by electrolysis.
Well, I don't know how
the flow is uniform and laminar. Layers near the plate, the velocities are much lower. Narrow boundary layer region. The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth.
Okay, now the coordinate frame that I'm unable to remove. Let's see. No. The control volume is fixed to the fluid. So that means that there is no fluid motion relative to the control volume. Therefore, there is no advection heat transfer in this Lagrangian coordinate frame. In this case, it's the same problem as before, but because what we move is the plate instead of moving the fluid, the transport of heat or momentum, but let's worry about heat in our class. The transport of heat when the fluid is not moving relative to the control volume will not involve advection. Very important because we will use this to do some, to skip many steps in math. So we don't have advection, but we still have conduction. And if we have conduction, we are going to have a transient. And when this video says the thickness of the boundary layer increases with time, what it's talking, in this case for fluid mechanics, how the momentum is penetrating into the fluid, penetrating from the, is penetrating from the surface of the plate that is moving and imposing momentum, penetrating deeper and deeper into the fluid. In this aspect, the fluid is behaving very much like a semi-infinite solid. And that's why on Monday, I took a special time to go over the semi-infinite solid. I'm going to go over this concept again in a minute.
The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow.
Okay.
The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer.
You have seen schematics like this, like I did towards the end of Wednesday's class, in which if this line that divides light and dark, this is the surface of the plate. And if we pick one point on the plate, let's say this, then we can make this graph. There is a graph that has the axis tilted, right? This vertical line represents the y-axis, the axis perpendicular to the surface. But this horizontal line doesn't represent distance anymore. This represents velocity. And this arrow here, this U, indicates velocity at different points. Velocity, and this line indicates what the end of the arrow would be, and says that far from the plate, we would have a velocity that is what we call U infinity. And near the plate, the velocity gets smaller and smaller. And in the case of viscous flow, on the surface, the relative velocity of the fluid at the plate is zero. The fluid is stuck to the plate. And you see, I mentioned last time, I used the term YCT or YCV for the concept of the boundary layer, the thickness of the boundary layer, because there are other ways of defining it here. You realize that this definition of boundary layer delta is not based on the tangent that we use. There are good reasons why they use it, and there are good reasons why we use the one we use. And those reasons are the reasons you're gonna like, because it makes our math a lot simpler. Okay, so thickness of boundary layer. I want to show you one case in which the thickness of the boundary layer matters. We have talked about chip cooling quite a bit in the assignment. We have talked about chip cooling in many examples during the class. If we have a heat sink that has many pins, the fan is moving the air through the pins. But think of this. Around each pin, we have a boundary layer. So you might wonder, why don't we put more and more and more and more pins? If I have more pins, I would cool more. And what's the secret? If I put the pins too close to each other, the boundary layers in which the fluid is not really moving and transmitting heat by conduction that is very slow instead of advection that is very fast. If the pins are too close to each other, they don't need to be touching. But if their boundary layers touch, then we killed all the heat transfer. That's why these pins are this close. If they put them any closer, the boundary layers touch and heat transfer crashes. If they put them more separate, they're losing money, because if they are too separate from each other, you have too much area with too few pins, right? So you try to cram the pins as much as you can, but the limit is given by these boundary layers. This is super interesting. So, okay. Let's go to let's see if I can, dang, here. Huh. Okay, good. So we did talk about these thermal boundary layers, and we know from before that the thickness of the boundary layer is related to the heat transfer coefficient in this way. That is, thickness of boundary layer is thermal conductivity of the fluid divided convection coefficient. And we saw this many times. I even reviewed it on Wednesday. I'm not going to review it again, but this relationship is important. We also mentioned that the concept of boundary layer only makes sense when the boundary layer is thin, because when the boundary layer is very thick, the problem becomes a problem of conduction, not a problem of convection. And what would be the condition to say that the characteristic length of our body is much bigger than the boundary layer? And this ratio, that is a dimensionless number, one length divided one thickness, units cancel each other, we call that the Nusselt number. That looks very much like a Biot number, but it has nothing to do with the Biot number other than both involve convection. And then I made this a really complex graph that now looks like the artwork of a madman, and maybe it's true. But as I was doing it step by step, I was trying to make this other pretty ugly drawing here to be more clear. So what was the story here? That I'll try to do it again quickly, and let's see how I'm doing with that. So we said we have the flat plate that we saw in the video. And we have our fluid flow, right, at U infinity and at T infinity, and the plate is at a surface TS, right? And we said we can pick one point. Let's pick this point. And in this point, I'm going to do a new, and at that point, I'm going to graph in this direction velocity, and in this direction, this is the y coordinate. Right here is the surface of the plate, right? And we said we know that that far from the plate, we are at U infinity. And we know that far from the plate, we're at U infinity. We know at the plate, we are at velocity 0. And we would have this sort of velocity profile. And very, very often you're gonna see in the books how they put like these arrows here indicating the velocity. And we said, using our definition of boundary layer, that if we prolong the tangent, this thickness is what we are going to call characteristic distance, thickness, characteristic distance in y, and this is for the velocity. And we said that for the boundary layers, we have two different boundary layers, and could be one is thermal, one is viscous, and one, let's consider the two extremes. in which one of the boundary layers is much bigger than the other. Depending which one is which, is the extreme. And we decided to start with extreme, in which the thermal boundary layer was a lot thicker, right? So much thicker than we can even forget the thickness of the viscous boundary layer. So I made this, let's make a new drawing. And again, this is if we go to this one point on the plate, I'm going to make then the y coordinate just as before, but now I'm going to graph in this horizontal axis, I'm going to graph temperature, not distance x. This is temperature, and this is this axis is temperature that corresponds to the distance x. Where is distance x here? Let's mark it. Distance x starts at the leading edge and moves downstream. Okay, so what do we know? We know that in contact with the plate, we're at temperature Ts. So at y equals 0, we have Ts. And I'm keeping an eye on the chat. And I don't see any questions. And last time I didn't see any questions. And you know what that means? Either of these two extreme things. I'm explaining everything totally clearly, or nothing is coming across clearly. And I'm afraid. Because this is very difficult. So I would imagine I'm being less clear than usual, not because I mean, but because the topic is more difficult. So if something is confusing, please let me know. And today we're going to have office hours too, where I hope we can discuss more of these. Okay. We also said that the fluid far from the surface is at temperature T infinity less than Ts. And so we would be here. Let's do this right. Right. But we go from the surface to this position far, we would go like like this curve here. Right? And if we do our old trick of keeping with the tangent from the beginning, right? Where this crosses, and this is what we're gonna call YC thermal. And if you remember, the YC viscous was another thickness that was much smaller. So what do we see that I mentioned at the end of class last time? We see that this point here has velocity u infinity. This point here has velocity u infinity. This point here has velocity u infinity. And you might wonder, how do I know? Well, I know because anything that is thicker than YCV is at essentially y infinity. Only here we would have velocities that are less than y infinity, than u infinity. Only in this region. And I said, in this extreme case, it's so small that we're not going to worry about it. So let's see if I can do magic for you today. because actually this is magic. It's awesome. So here we have our plate, and we have, let's make a control volume. Okay, before I make a control volume, let's draw the boundary layer. And we said that the boundary layer is thin, right? If you remember, when we talked about heat transfer mechanisms in our second week of class, we said that there were many ways of simplifying a problem, and one of those was due to geometry. So we have something that is very thin, but also very long. We could neglect, we could have conduction in this direction was important, but conduction in the other direction was negligible. Because it's thin. In addition, something we also saw on the when we discussed also in the second week of class, and also we saw it again when we discussed differential control volumes in week 4, was that if we have a fluid flow and we have conduction at the same time, and this is the part of what was in our quiz 2, if the Peclet number is high enough, then we can forget about conduction in the direction of the flow and keep only advection. So there are many reasons why, in this case, we can neglect conduction in the X direction. There are many reasons. But look at this, how awesome. Let's say I make a control volume here. Let's make it in green so it's less confusing. So let's make a control volume here. It's a differential control volume, right? And this control volume, right, has conduction in this direction and has only advection in this direction. So conduction in the y direction, because there is no motion perpendicular to a plate, but there is advection parallel to the plate. And conduction was negligible because of many reasons. One is very flat, very thin and long, because the fluid flow under normal conditions, which we're gonna double check, means that Peclet number is so large that we can neglect conduction in the x-axis. So far, so good is what we have seen. What I'm going to do next is where it gets interesting. What I'm going to say is okay, this control volume that was fixed to the plate, let's now let this control volume move in the direction of, let's have this control volume move in the direction downstream with velocity u infinity. By saying this in proper mathematical terms, what I'm doing is changing my control volume from being an Eulerian control volume that is fixed to the plate, like some of the videos we saw at the beginning, to a control volume that is drifting downstream together with the flow, like the last part of the video we saw. Why this matters? Because, I have a question. If I could explain why the whole plate doesn't have conduction, but we have conduction in the CV. So what I'm going to ask is if you can rephrase the question. I didn't understand what CV is, and I didn't understand what talking about conduction in the plate, because I'm talking about all this conduction we're talking about is conduction in the fluid. And I really want to answer this question. So, and I hope it helps everybody. So, plate doesn't have conduction. So I think the question is, I'm going to rephrase the question the way I think I understand it, is if I can explain again why there is conduction in the direction of y, but no conduction in the direction of x. And the reason is that in the y direction, the fluid is moving left to right. And as it moves, it transports heat by advection. But the fluid is not moving up and down. And so we have zero to or negligible advection vertically. However, we have a gradient from Ts to T infinity going across the boundary layer, and that goes by conduction. But the fluid that is moving, the heat transfer in the direction of the flow is dominated by advection. We saw that twice when we studied conduction in week 2 of class, and when we studied differential control volumes in our 4th week of class. So please take a look about the effect of Peclet. So it comes down in mathematical terms to say Peclet is large. And in intuitive terms is if the fluid moves fast enough, that means if U infinity is fast enough, that overtakes, the advection overtakes conduction. I hope that more or less answers it. And if not, we can continue in the office hours. So what I'm doing next is moving the control volume downstream. This little trick unlocks everything and is extremely powerful. Why? Because if I have this Lagrangian control volume that is fluid moving downstream with the flow, there will be no flow crossing the control volume. Why not? Because the fluid is moving, the control volume is moving with the fluid. So the fluid never gets into the control flow, never gets out of the control flow, because the control volume, the fluid never gets into the control volume, never gets out of the control volume. So it just drifts down with the flow. But if I said I have no conduction in X, right? For many good reasons. And now I say, okay, I have no advection because I'm moving down. I'm being left with a system in which really there is no heat transfer in the X direction. And this is the key. There really is not heat transfer in the X direction. We have all the heat transfer in the Y direction. And what happens then is that in Lagrangian coordinates, the system became a transient system, right? We don't have heat transfer by conduction in this direction. And if I have Lagrangian coordinate frames, I don't have heat transfer by advection either. I have heat transfer in the Y direction, and it's a transient in this control volume. I would have conduction heat transfer in the fluid in the Y direction. That means 1D heat transfer, and it's transient. I could write down the partial differential equation for that. And the partial differential equation is this one here in equation 8, is variation of temperature with time. That's the transient term, equals alpha second derivative of T with Y. Right, the Lagrangian, this is assuming constant thermal conductivity. Do you remember having seen this? This is what we saw on Monday. This is the same equation as the semi-infinite plane. And it's going to have also a boundary condition far away that is T equals T infinity. It's going to have an equation of initial condition that is T equals T infinity. because that's the velocity with which the flow was coming and the flow is away. In a semi-infinite solid, we would call it Ti or T naught. In this case, everything that is far, we call it T infinity. And then we needed another boundary condition in Y, right? You see the second derivative, and can be constant surface temperature of the plate, or can be a constant heat flux from the plate. Same as a semi-infinite solid. So now, let's say we consider the boundary condition of constant surface temperature of the plate. And this is amazing because this equation with those boundary conditions, we had already solved for the semi-infinite solid. Actually, we didn't solve. We knew it was this error function that somebody somehow did it during a PhD, and we all gratefully take, and we don't need to do again, but we know the solution. And we know the solution for the penetration of heat into a semi-infinite plate. We discussed that on Monday, and it seems like a year ago because we're piling up so many concepts. But the penetration of heat into a semi-infinite plate was square root of pi square root of alpha t. It's in the notes, right? Right now you might say, well, I don't remember how it came. You might remember that I said often, pay attention to the square root of alpha t, right? Because it appears all the time. And this square root of pi is the value that was more or less 1.5, right? It was 1.77 in this case, but other case was something like 1.12. But the dependence on square root of alpha t is always the same. So all of a sudden, now I have this, I can estimate the thickness of my thermal boundary layer because I know the semi-infinite solid. And although boundary layers, we typically don't use time because the boundary layers we analyze are in steady state. But funny enough, is steady state in Eulerian coordinates, right? In Lagrangian coordinates is transient, but in steady state, in Eulerian coordinates, if I keep my eyes on the plate, nothing changes. And there is a relationship between space and time because this the fluid is moving at constant velocity. That is, distance x equals u infinity times time, and time 0 is when it first hits the plate. So I can replace this equation we had for the semi-infinite plate, the square root of alpha t, and instead of writing t, I'm gonna write from equation 7 here, x over u infinity. And this equation 10 is the thickness of the thermal boundary layer. If you wanted to do it, if instead of being an engineer, you were a physicist, you need to solve the Navier-Stokes equations, which are two coupled equations that are partial differential equations, nonlinear. They have 4 unknowns. You have 2 velocities and a temperature and pressure. So you need another equation that is equation of continuity. That is another partial differential equation. And then you need a 4th equation that is also a partial differential equation, that is equation of energy. That's how physicists would do it. That's how a mathematician would get a PhD. And for us, because we knew the semi-infinite solid, now we can just cut across all that and say this. And by the way, this I'm putting here, equation 10, is the exact solution. No simplification. No simplification other than saying that the boundary layer is thin. That is the same simplification that the mathematicians do. This equation 10 here is what a mathematician would give you after 4 years. In our case, was 43 minutes. I feel good about that. So, now that I have the thickness of the boundary layer, if we remember that the ratio between a distance and the thickness had to be large, meaning the boundary layer was small, and that was called the Nusselt number. Here you have Nusselt number. You see this little x here means Nusselt number in which the characteristic distance is x. If I have a cylinder, probably I would call it Nusselt d, because the characteristic distance will be diameter. So I do x over yct, and I can get this expression for Nusselt, which you're going to see we use Nusselt all the time later on. Right now, you might be wondering, so what? Also, because I know, and because you use this in quiz 2, you know how to calculate h. Is k over yct, right? The k over the thickness of the boundary layer. And here we have an expression for h. This is so powerful. If you think, up to today, I've been giving you numbers for h. I've been saying, oh, if it is air, stagnant air is 10, if it is forced air is 100, if it is water, if it is forced water. I was giving those to you, and you were taking me on faith and your kindness. And now you can calculate it. You can say h, haha, you give me the thermal conductivity of the fluid, whatever the fluid is, give me the velocity of the fluid, and give me the distance at which we are. And what do we see? We see something interesting. We see that the convection coefficient depends on the place we're talking about. This is what is called the local convection coefficient, local H. Often we use an average, and there is some notes. If you please take a look at the notes here, there is a difference between using the average or the local value. We see something else, that x, when x tends to 0, h tends to infinity. I think I have a graph here. Here we have yct that has this shape of a square root, and h has an asymptote near 0. Now, of course, infinity doesn't exist in reality. What happened? Well, when x tends to 0, my Nusselt number would tend to 0. And we said all along that all this analysis is good for Nusselt numbers that are large. If the Nusselt number is small, I have to do a different analysis because it becomes a conduction problem. So this asymptote here, I have no problem with it because I'm actually not talking about x tends to 0. But I know this. This is the leading edge. This says so many things. For example, what do we learn? You see this formula H depends on U infinity. Higher H means higher heat transfer. And this is a reason why stagnant air at low velocities has a small h, 10. But forced air at high velocities has a higher convection coefficient, right? Let's call it 100. It's right here. It's right here. It's telling us the effect of velocity. Isn't this amazing? Because you knew the effect of velocity. You didn't need to take this class to know that it's colder when it's windy. But now you know exactly what the mechanism for that is. I'll tell you more. If it is windy and you face the wind, you're going to feel the cold in the front of your face. If you turn away from the wind, it's not going to be as cold. And this formula also says it. Of course, most of our faces are not flat plates, right? But the concept will still stand. At the leading edge, x is small and the convection coefficient is high. Here our formula says infinite, but of course it's not infinite, but that is high for sure. That's why we feel more cold, because the boundary layer is very thin at the leading edge. When the wind hits our face, the boundary layer is very thin, therefore our layer of protection, our invisible layer of thermal protection is very thin and we feel the cold. If we turn around and we face the opposite way of the wind, we would be having our face farther downstream after the boundary layer has developed. And the boundary layer is thicker, so we have more of an insulation layer. It's all in this formula. It's all in this formula we did together. It's all in this formula that comes from 4 coupled nonlinear partial differential equations, which we did not do, just because we were smart enough to combine our Eulerian coordinate frame and Lagrangian coordinate frame, remember the semi-infinite solid, and combining things that seem to be unrelated to each other. All of a sudden, we put them together, and we got from a box of parts to have a Swiss watch, right? This is quite awesome. Before we finish, we have a minute. How do we tabulate convection coefficient? Because this formula is true. This formula is true, but is of a but it is based on age, but will depend on it's difficult to tabulate. How do people tabulate it? So it's useful for everybody else. They tabulate it using nu. So instead of writing age, for whatever reason, but you're gonna see it's helpful, instead of writing age in the heat transfer book, they write nu. And of course, to get h, we have to multiply Nusselt by k and divide by the characteristic length. And when we do that, we're gonna see that dependence of nu is on Reynolds and the Prandtl number. This is just a manipulation of variables that I don't want to do now because we're already run out of time, but it's a manipulation of variables that I would invite you to do. It's done in this handout, and you can follow it. So this formula we have just derived together, the formula that comes from 4 partial differential equations that are nonlinear and coupled, and gave us a value of h that is a square root, 1 over square root of x and that stuff. If I do this change of variables, instead of using h, I use Nusselt. Instead of using u infinity and x, I use the Reynolds number and the Prandtl number, I would have this expression. And this is how it is tabulated in every heat transfer book. And this is the exact solution. And this solution will appear in the book we have, this one. And they don't tell you how they got it. I'm telling you, we did it together. What we are going to do on Monday is to go over a few more of these things with external flows. And around Monday, we should be done with external flows, maybe Wednesday, we'll see. Let's stop here. I wish you a great weekend. I'll take a 8-minute breather and see those of you who want to join me for the office hours at 2. Thank you.